This next test that I'm going to show you, it's called the AKS Test, okay? And the AKS Test, does anyone know what it stands for? Anyone? Anyone? If you're observant, you'll know. AKS, it stands for Agroa Kayal Saxena. Just like before, 3 mathematicians. The AKS test, right? It's a massive, massive improvement on Fermat's test, as you'll see, okay? And it also has some kind of cool implications, right? So here's the way it works. Let me write it out for you first, and then we'll unpack it, okay? Again, we're testing a number, P. Is P prime? Okay? It sounds, as I go through it, remarkably similar to Fermat's test, okay? Here's what we're going to calculate. X minus 1 to the power of P, and X is not a number, it's going to be, we just leave it as a variable, okay? And we're going to subtract X to the power of P minus 1, okay? So when you do this, so this is a polynomial, you've got to do some expansion of the brackets and all that kind of thing. When you get a result out the end, and then you do this and you simplify, okay? There's going to be a whole bunch of coefficients within the polynomial, okay? You remember what coefficients are for something like, say, this? Okay? Your coefficients in this case would be 1, 5, and 6, okay? So when you expand this out for some number, P, you will have coefficients like this, okay? So what you want, the way to know whether P is prime or not, is that all coefficients, every single one, will be, just like with Fermat's test, multiples of P. Okay? If P is prime, then when you evaluate this and you simplify out, all the coefficients will be multiples of P. All right, let's test it out, shall we? Let's start with a, because we're doing an expansion here, we'll start with an even smaller prime number. Let's go with 3, because that's small enough to be workable, but large enough to be interesting. Okay? So we're going to test P equals 3. Okay? So I'm going to write out x minus 1 cubed, right? Minus x cubed minus 1. It has this kind of neat symmetry to it, which is nice. The whole powers and the brackets and the subtraction as well. So let's evaluate this thing. Okay? Now, you can go ahead and you can actually, you can expand this out. You can say, well, that's going to be x minus 1 times x minus 1 all squared, which is, it's a perfect square. So that's a known result. So you can, that's a plus 1. That's a known result. So you can go ahead and do that. But there's another trick you can use. If you go ahead and you do this, what you'll end up with is, I'll make sure I get my numbers right. What you'll get is these numbers here, 1, 3, 3, 1. Does anyone recognize them?
It's Pascal's.
Aha, okay. So if you draw Pascal's triangle, ta-da, there are the coefficients right there. Okay? So that's where the numbers are. Don't forget there's signs in here, so watch out for those. All right. Now I can do this subtraction business at the end. Okay. So what am I going to end up with? Let's see here. I lose the x cubed at the front, so that's going to go. And there's a negative 1 here. Take away negative 1. So those are going to go. Yeah? What are we left with? We're left with this guy, and sure enough, all of the coefficients are multiples of 3. Yeah?
What happens if they're negative numbers?
Okay, so for the purposes of this test, it doesn't matter that they're negative
No,
numbers.
I mean,
Okay?
what if the prime number that you're trying to test if it's prime is negative?
Yeah, we don't really tend to talk about negative numbers when we're considering primes. We're really in this territory, okay? Because when we're thinking about divisibility is a bit weird when you think about negative numbers. Because then think about this, right? Is 5 prime, right? It's like, well, its factors are 1 and 5. Ooh, but wait.
Negative.
What about negative 1 and negative 5? Now I have more factors. Oh no, my universe. Okay. So for that reason, we don't really consider negative numbers as part of the equation. Does that make sense? And it's not arbitrary, it's just not particularly useful to consider that. Okay. So, let's give this a go. Just interestingly, oh, Lewis, yeah, just stretching. Let's just go to the next one, right? Have a look at this. 1, 4, 6, 4, 1. Okay, 1, 4, 6, 4, 1. That's the next row, right? So when you think about the next test, when you do this out, this is testing if 4 is prime. right? Have a look at the numbers. Are all of these coefficients going to be multiples of 4? And the answer is no, because 4 is not prime. 4 is composite, right? Have a look at the next row. It's Pascal's triangle. You can work out the next row for me, can't you? 1, 5, 10, 10, symmetry. So when I do this process, right, you see what this does here. What does this do, right? If we were doing this test for p equals 5, all you're doing really is you're taking off the first one and you're taking off the last one, right? So really all you're doing is this.
Yeah.
So another way of saying the AKS test is, rather than going through and thinking of polynomials, right? Another way of saying is p prime. Is p prime? Well, is the pth row of Pascal's triangle, is it full of multiples of p? And if it is, it's prime. Okay? Let's just go on a little bit and see what happens. Like if I go to the next row, it's going to be 1, 6 will be here, right? 6, what's the next one? 15, and then 20, and then symmetry, right? So are all these numbers multiples of 6? Of course not, because 6 is composite, right? But then, look at the next row. Come on, give it a go. 1, 7, 21, 35. Oh, are you serious? Yeah, you bet I'm serious. Okay? If you really want, go ahead to row 11 just to freak yourself out. Okay? It's pretty profound. Now, here's the really cool thing. Two things. Number one, you kind of took it for granted. I went from this line to this line, right? And I just told you that was the coefficients, okay? Just to be content, you go ahead and take this thing. It's not that hard. There's only going to be 6 terms which will collapse into 4, okay? Just satisfy yourself that that really is what the expansion is, okay? So weird thing number one is, why should these coefficients end up as these numbers? The second thing is, right? So after you establish that, well, why are all of these numbers multiples of 7? And when we get down to the 11th row, why are all of these numbers going to be multiples of 11? Now, if you hold on for the next 2 years of maths, not that it's part of the syllabus, but you will learn the maths that will help you solve and prove why these are multiples of, it's going to be multiples of 11, multiples of 13, multiples of 17, and on and on and on. It's quite profound. Okay? So you can see the AKS test, massive improvement over Fermat's test, right? Much, much faster.